All right, so some of you guys were asking about trigonometric equations and trigonometric identities. So I'm going to try to just give you an overview of that, and then in another video I can do some more specific examples. But here's the big basic idea. The basic idea is that we're talking about right triangles. We're talking about right triangles with a certain angle right here. You can call that angle theta, you can call that angle x, or angle A, whatever you want. But when you set up those right triangles, you end up getting, with this right triangle that has a hypotenuse of 1, you can say that sine is opposite over hypotenuse. So the way this triangle is set up, that would be like your y value over hypotenuse of 1. The cosine is the adjacent over hypotenuse, so that's just x over 1. So what that simplifies down to be is just that the sine is equal to the y value on your unit circle, and the cosine is equal to the x value on your unit circle. And then if you remember from SOHCAHTOA, the tangent part is just opposite over adjacent, which just means that tangent is equal to sine divided by cosine. And then there's one other thing that we can do with this basic triangle, which is that we know that every time there's a right triangle that a squared plus b squared equals c squared. On this one, our a and our b and our c, we labeled them as x and y and 1, so we call that x squared plus y squared equals 1 squared. But we also have another word for x. We know that x, right here, is the same as cosine. We know that y, right here, is the same as sine. And so then we get the Pythagorean identity. It's just a squared plus b squared equals c squared, but it's just rewritten for a triangle that has a hypotenuse of 1. The reason I keep saying unit circle, I haven't explained that, is if I put those axes on there and if I draw a circle that has a radius of 1, pretend that's actually a circle, anywhere that I go one step away from the origin, I can consider the angle, and I can talk about x being the cosine and y being the sine. And so that's where we're going with the sine and the cosine. Okay, now here's the big idea. Because we can go around and around the circle, we start here at 0 and we go around the circle counterclockwise, and we can do that as many times as we want. If we were trying to solve a particular equation, we would get an unlimited number of solutions. So, for example, if I was trying to solve the equation where like cosine of theta is equal to 1, that means where does the x value on the unit circle equal 1? Well, that equals 1 when I go completely to the right here. So that happens right at the beginning of the unit circle, but it also happens after I do a full rotation. So another possible answer is 2 pi as a full rotation, or 360 degrees. And I could do another full circle. So it could be 4 pi, or 6 pi, or 8 pi, etc., etc., etc. It gets even a little trickier when you're doing things like, instead of equaling 1, which is on the very edge of a circle, let's say I was going to equal 1/2. A triangle where the sine is equal to 1/2 looks like this. We've got a short and wide triangle. That happens at 30 degrees, which is written as pi over 6. But it also happens over here in quadrant 2. In quadrant 2, we have the same triangle just reflected. The y value is still positive 1/2. And so that's a little bit less than a half circle, which is 5 pi over 6. The way I do this is, we know that 0 is the beginning, and we know that 2 pi is a full circle, meaning that 1 pi is half of a circle. So if I know that my solution is pi over 6 in quadrant 1, I know that I'm pi over 6 away from a half circle. So I took away pi over 6 from pi. I took away 1/6 from 1, I got 5/6 left over. Now, are those the only two solutions? No, there's an infinite number, because I can go back around the circle, back around the circle, back around the circle. And each time I go around the circle, I'm adding 2 pi. So think about fractions. 2 pi, 2 is the same as 12 over 6. 12 sixths is the same as 2. So I'm going to take each of my first two solutions. I'm going to add 12 sixths to it. So 13, because I did 1 plus 12, and 17, because I did 5 plus 12. And you could keep going as much as you want. You can also go into the negatives, okay? So anytime that you're solving an equation in here, start with the solutions that are on the first rotation of the circle, and then just add or subtract full circles to get the rest of the solutions. And just make sure you're thinking about common denominators. If I'm adding a full circle and I have a pi over 6, that means I'm adding 12 sixths to it over and over again. Okay. Now these equations can get a little more complicated to the point where we need to use some trig identities to solve them. So we already have our basic tools. We know that tan is the same as sine over cosine, and we know because of a squared plus b squared equals c squared, we know that cosine squared plus sine squared is equal to 1. So those are your main identities that you're going to use in a lot of these problems. Let's see if we can get an example here. And we have some other identities that I want to do. So the double angle identity, etc. Okay. So basically, there are these rules that you can use for things like cosine of 2 theta and sine of 2 theta. And I can prove these to you, but we can also just use these formulas. They're in your formula packet. So the cosine of 2 theta has actually 3 different ways of writing it in the formula packet. You can write it as cosine squared theta minus sine squared theta, or you can write it as 2 cosine squared theta minus 1, or you can write it as 1 minus 2 sine squared theta. This is usually the version of it that I remember right here. The other 2 versions come from using this Pythagorean identity and substituting it in right here or right here. So let me be a little more specific. If I take my Pythagorean identity, I can say that cosine squared is 1 minus sine squared, just by subtracting sine squared from both sides. And so if I say cosine squared is 1 minus sine squared and substitute that in, I get this third version of it. I've got 1 minus sine squared minus another sine squared. If instead of rearranging that formula as cosine squared equals 1 minus sine squared, if I just take this and swap it, so I solve for sine squared is 1 minus cosine squared, and I substitute that right here, then I get this formula. Okay? Now sine of 2 theta also has a nice formula, which is just 2 sine theta cosine theta. And again, these are things that we can prove by drawing some triangles and finding the areas of them, or just looking at the angles. But for the purposes of this video, for the purposes of the test, these are just things that you are assumed to know to be true. You're not going to have to prove them. You just pull them out of your formula packet and use them. So using all of those things together here, you can do some different things like find an angle that you want to know. So for example, let's say that I wanted to find the value of sine of 15 degrees. Okay. Well, what I can do is I can say that sine of 15 degrees is related to, I could use either cosine or sine. I'm going to do cosine. I could use the cosine of 2 times 15. And the reason I'm doing 2 times 15 is because I know what the cosine of 30 is. So the cosine of 30 degrees is the same as the cosine of 2 times 15. But if we use cosine of 2 times 15, I can rewrite that in terms of sine. So I'm going to back up again and just sort of restate the question. The question said, figure out what sine of 15 degrees is. And 15 degrees is not on our unit circle, so that's why we're using our identity here. And I say, okay, I don't know the sine of 15 off the top of my head, so I'm going to relate it to a known angle. And I know the angle 30 degrees. And so I'm using the double angle for cosine to relate it back to the question. So using this identity right here, we can say cosine of 2 times 15 is the same as 1 minus 2 times sine squared of 15. Okay? So cosine of 30 is the same as 1 minus 2 sine squared of 15. Well, the cosine of 30 off your unit circle is square root of 3 over 2. Now all I'm going to do is solve for sine of 15. So I got to subtract 1, divide by 2, or divide by negative 2. So now I have negative root 3 over 4, and positive 1 over 2 is equal to sine squared of 15. And then I take the square root. And when you take a square root, you get a plus or minus. So we'll talk about that in just a second. I'm going to do a common denominator. So I'm going to make the over 2, the 1/2, into a 2 over 4. So I have negative root 3 plus 2 over 4 is going to be sine of 15. And now I think about, is it going to be a positive or a negative? Well, 15 degrees is in the first quadrant. And so this is going to be a positive square root. So my final answer is just the square root of negative root 3 plus 2. And the square root of 4 on the bottom is 2. And there you go. You could also write that as on the inside, instead of negative root 3 plus 2, you could call that 2 minus root 3. So that's sine of 15. Okay. So that's one kind of use of these identities. Another use of these identities is when you are trying to solve an equation. So let's look at an example there. Let's say that I'm trying to solve an equation like 6 sine x cosine x is equal to 1. And I want to find answers that are between negative pi and pi. Well, I can't really do anything with sine times cosine. If it was sine divided by cosine, I could write it as tangent, but it's sine times cosine. But I remember my double angle formula. I remember that 2 sine x cosine x is the same as sine of 2x. So the original equation looks a lot like the double angle formula. It's just 3 times bigger. So I have 3 times the sine of 2x is equal to 1. Divide by 3. So I get that the sine of 2x is equal to 1/3. That's not a special unit circle one, so I'm just going to use my inverse on here. Second sine inverse of 1/3, just like that. So now I know that one of my solutions is when 2x is equal to 0.3, and then if I round it up, it goes to 340. So one of my solutions is divide by 2, 0.170. Yeah. Okay, but that's only one of my solutions. If you think about on the unit circle, where sine is equal to 1/3, it's here, but it's also here, just like I talked about earlier. So my other answer is that 2x is equal to pi, because that's a half circle, minus 0.340. So I go pi minus 0.340, which is 2.8-ish. Divide that by 2, and you get your other answer, that x is equal to 1.400. Okay? Now, we got to be careful because we found two answers that are smaller than pi, but did we find any answers on this set of things? What we can do is go back to our idea from earlier that you can take a number on the unit circle and you can add or subtract a full circle, add or subtract 2 pi. And so that's going to give me two more answers. I'm going to go the inverse sine of 1/3 minus 2 pi, like that. Divide that by 2. So I get a third answer of negative 2.972. That's less than, or let's get bigger than negative pi. And then my other one, I have pi, oops, uh-oh. Oh no, okay. I have pi minus 0.340 minus another 2 pi. I could have simplified that. So there, dividing by 2, and I get negative 1.741. All right, so I'll do another video. I didn't really do very many trig identities in this one, so I'll do another video in a little bit where I go over some trig identities.